closely at the food you eat, the clothes you wear, and the materials in your home. The chemical foundation for all of these things relies on a single element, carbon. Despite building nearly everything we use, carbon is remarkably scarce in the natural world. It makes up just 0.02% of the Earth's crust as minerals, and 0.03% of our atmosphere as carbon dioxide. To access this limited material, humans have spent centuries digging deep underground. Fossil fuels like coal and petroleum are essentially massive reserves of compressed ancient carbon trapped in the crust. This gap between carbon's scarcity in nature and its abundance in our lives points to the way its atoms are built. To see how carbon forms so many connections, we have to look at its atomic structure. Carbon has an atomic number of 6. That means it has 6 protons in its nucleus, surrounded by 6 electrons. 2 of those sit in the inner K shell, leaving exactly 4 valence electrons in the outer L shell. Like all elements, carbon's reactivity is driven by a tendency to reach a stable noble gas configuration, which requires a completely filled outer shell of 8 electrons. Carbon sits in the middle of the periodic table, possessing exactly half of the electrons needed for a full outer shell. This specific count creates a dilemma when it comes to standard chemical bonding. Most elements achieve a full shell by transferring electrons, either gaining or losing them completely to form ionic bonds. Let's see what happens if carbon attempts this. First, it could try to gain 4 extra electrons to form a C4- anion. However, the nucleus only contains 6 protons. That positive charge is not strong enough to hold on to 10 total negative electrons. Alternatively, it could try losing its 4 outer electrons to form a C4+ cation. But stripping away 4 electrons requires a massive amount of energy, leaving a nucleus with 6 protons struggling to hold just 2 electrons. Because electron transfer fails both physically and energetically, carbon is forced to find an entirely different mechanism to achieve stability. Carbon overcomes this problem by sharing its valence electrons with other atoms. These shared connections are known as covalent bonds. The simplest example of this is between 2 hydrogen atoms. Each has 1 electron, but needs 2 to fill its shell. By overlapping, they share a single pair of electrons, creating a single covalent bond. An oxygen atom has 6 valence electrons and needs 2 more. When 2 oxygen atoms meet, they each contribute 2 electrons to be shared, resulting in a double bond. Nitrogen atoms have 5 valence electrons. To reach an octet, they share 3 electron pairs between them, forming a triple bond. The number of shared electron pairs between atoms directly dictates whether the resulting molecule features a single, double, or triple covalent bond. Let's apply these rules to a multi-atom molecule, water, or H2O. Pause the video here. Draw the electron dot structure for water, and see how oxygen and hydrogen can mutually satisfy their valence needs. Here is the correct structure. The oxygen atom forms 2 separate single bonds, one with each hydrogen atom. This arrangement satisfies the shell requirements for all 3 atoms involved. These internal sharing arrangements define the physical properties we observe in the laboratory. This table shows boiling points of carbon compounds. Methane boils at 111 Kelvin, ethanol at 351. These are notably low compared to ionic compounds. While covalent bonds inside molecules are strong, intermolecular forces are very weak, requiring little heat to break apart. Because no ions are formed during electron sharing, covalent compounds are generally poor conductors of electricity. To recap, ionic bonds rely on electron transfer, while covalent bonds rely on sharing. This sharing mechanism allows carbon to build stable molecules with low boiling points. Furthermore, since sharing doesn't create charged particles, or ions, these covalent compounds cannot conduct electricity. Now that we understand the mechanism of the covalent bond, we can look at the massive variety of shapes carbon can build. Next, we'll explore the structure of methane and the different forms of pure carbon. Carbon has 6 total electrons, but only 4 sit in its outermost shell. To reach chemical stability, it needs 4 more. Hydrogen, however, has 1 electron and only needs 1 more to fill its shell. We can see how they solve this problem together in this diagram. A single central carbon atom takes its 4 outer electrons and pairs them up with the single electrons from 4 separate hydrogen atoms. By sharing these pairs, everyone achieves a full, stable outer shell. This is methane. While we usually draw this flat on paper, electrons naturally repel each other. In real space, these 4 bonds push apart as far as possible, pulling the molecule into a 3D pyramid shape called a tetrahedron. Because carbon has this specific, rigid capability to form exactly 4 bonds, we call it tetravalent. This requirement to form 4 bonds serves as the structural foundation for carbon's behavior. Every complex arrangement we study starts with the atoms satisfying this specific count. So we know carbon always forms 4 bonds to reach stability. But that raises an interesting question. What does carbon do when it is completely isolated, bonding only with other carbon atoms? This animation shows one possible answer. Here, every single carbon atom uses all 4 of its available bonds to lock into 4 other surrounding carbon atoms. As this pattern repeats, it builds a massive, deeply interlocked 3D framework. There are no loose ends and no weak points. The result is diamond, the hardest naturally occurring substance on Earth. But look at this second structure. Each carbon atom only forms bonds with 3 neighbors, leaving one valency unsatisfied. Instead of a 3D grid, they form flat, repeating hexagonal sheets. These sheets stack on top of each other. Because the holding forces are very weak, the layers can easily slide past one another. That missing 4th bond leaves 1 electron per atom free to move horizontally between layers. This free movement makes graphite highly conductive, while diamond is an insulator. There is a third option. That same flat sheet of hexagons can bend, fold, and close in on itself to form a hollow, rotating sphere. This specific arrangement of 60 carbon atoms is called a fullerene. Whether carbon becomes an abrasive crystal, a slippery conductor, or a hollow sphere, the chemical element is exactly the same. The macrophysical properties of the material are dictated entirely by how the microbonds are allocated. Now let's look at carbon's ability to act as a universal building block, a property known as catenation. As we see in this animation, carbon atoms can link end to end to form incredibly long straight chains. From there, they can sprout perpendicular branches, creating highly complex molecular backbones. Let's test your intuition. Pause the video here and try sketching out what a molecule with 6 carbon atoms looks like if you connect the 2 ends of the chain together. If you drew a hexagon, you've got it. This is cyclohexane, and it shows that catenation includes forming stable, closed rings. These massive backbones do not break apart easily. Carbon is a physically small atom, which means its nucleus is very close to the shared electrons and can hold on to them tightly, creating strong, stable bonds with itself and other elements. This ability to link into any shape while maintaining high stability is why carbon can build more complex architectures than any other element. Let's lock in the core rules. As this split screen shows, the difference between carbon's main allotropes comes down entirely to bond count. 4 bonds give you a hard insulator, like diamond, while 3 bonds create a soft conductor, like graphite. The foundational rule is tetravalency, carbon's requirement to form 4 covalent bonds to reach stability, paired with catenation, the ability to link carbon atoms into stable chains, branches, and rings. Understanding how carbon manages these bonds allows us to predict the behavior of different molecular families, starting with the difference between saturated and unsaturated compounds. Carbon operates under a strict mathematical rule. To achieve a stable state, every single carbon atom must form exactly 4 covalent bonds. The constant drive to fill those 4 slots dictates the architecture of all organic chemistry. By sharing electrons through single, double, or triple bonds, carbon builds a vast variety of compounds. When building a simple carbon compound, the first step is to connect the carbon backbone. Here, we link 2 carbon atoms together with a single bond. Next, we use hydrogen atoms to satisfy the remaining empty valencies. With 6 hydrogens snapped into place, every carbon has its required 4 bonds. We've built ethane. Keep in mind that each of these solid single lines represents a shared pair of valence electrons between the atoms. Because we are only using single bonds between the carbons, this molecule is holding the absolute maximum capacity of hydrogen atoms. We classify these fully packed structures as saturated hydrocarbons, or alkanes. Notice the structural pattern. For any number of carbons in the chain, let's call it N, there are 2 hydrogens attached to every carbon, plus 2 extra hydrogens capping the ends. That gives us the universal formula for alkanes, CnH2n plus 2. Because all their valencies are satisfied by stable single bonds, saturated hydrocarbons are generally not very reactive. They provide the structural baseline for organic chemistry. But what happens when you run out of hydrogen? Here we have 2 carbon atoms, but only 4 hydrogens available. That leaves 2 valency slots flashing empty. To satisfy the 4-bond rule, the carbons compromise. They share an additional pair of electrons, creating a double bond between themselves. This forms ethene. If we strip away 2 more hydrogens, the carbons are forced to share 3 pairs of electrons. They pull together into a tight triple bond, forming ethine. Molecules with double bonds are called alkenes, and their formula drops the +2 at the end, becoming CnH2n. Triple-bonded molecules are alkynes, dropping 2 more hydrogens to become CnH2n-2. We classify alkenes and alkynes as unsaturated compounds because their architecture contains hidden capacity. If you were to break those multiple bonds, the carbon framework immediately has room to absorb more atoms. So far, we've constructed carbon chains in a straight line, like this butane molecule. Pause the video for a second. Try to draw a completely different shape using this exact same inventory of 4 carbons and 10 hydrogens. You can disassemble the straight chain, take an N carbon, and attach it to the middle. You've just built isobutane. These are structural isomers. They possess identical chemical formulas, but their physical architectures are distinctly different. Carbon chains can also curl onto themselves. A straight chain of 6 carbons can connect end to end to form a closed geometric ring, like cyclohexane. Just like chains, rings can be unsaturated. By shedding hydrogens and alternating between single and double bonds, the ring transforms into benzene. Carbon's ability to bond with itself creates straight chains, branch structures, and rings. The strict rule of tetravalency generates a massive catalog of distinct compounds. This table summarizes the rules. Alkanes have single bonds and a formula of CnH2n plus 2. Alkanes have double bonds and are CnH2n. Alkynes have triple bonds and drop to CnH2n minus 2. We can test these invisible geometric differences in a lab using bromine water, which has a distinct orange color. If you add an alkane, nothing happens. It's already fully saturated, so the liquid stays orange. But an unsaturated alkane or alkyne eagerly reacts. It breaks its multiple bonds to absorb the bromine, turning the liquid completely clear. The math of a molecule directly dictates its behavior. Whether a carbon compound has single, double, or triple bonds determines exactly how it interacts with the world. Carbon atoms link together to form stable chains. By replacing a single hydrogen atom on one of these chains with a specific cluster of atoms, represented here by the letter R, the identity of the molecule changes. This substitution mechanism allows a single carbon framework to take on a variety of different chemical behaviors by simply changing which group is attached. Elements like oxygen or chlorine replacing hydrogen are called heteroatoms. They act alone or in groups to change a molecule's properties. In haloalkanes, a halogen like chlorine or bromine takes the place of a hydrogen atom. Replacing that halogen with an oxygen bonded to a hydrogen, an OH group, creates an alcohol. If the chain attaches to a carbon double bonded to oxygen and single bonded to an OH group, it becomes a carboxylic acid. Both aldehydes and ketones contain a carbon-oxygen double bond, which often leads to confusion. The distinction lies in where that bond is placed. The aldehyde group is found at the terminal end of the carbon chain. The ketone group is located within the chain, bonded to 2 other carbon atoms. The functional group determines chemical reactions. A 10-carbon chain with an OH group participates in the same reactions as a 2-carbon chain. When we organize molecules with the same functional group but increasing chain lengths, we create a homologous series starting with methane. Adding 1 carbon and 2 hydrogen atoms, a CH2 unit, creates ethane, increasing the molecular mass by 14 units. Repeating this step creates propane. Because the change is consistent, we can use general formulas like CnH2n to determine the composition of any member in a family. Try to predict the next 2 members of the alkene family starting from ethene, C2H4. Following the rule of adding a CH2 unit, we get C3H6 and C4H8. This graph shows how melting and boiling points change as the chain length increases. As molecular mass goes up, physical properties show a steady gradation. Adding CH2 units changes these physical characteristics, even though chemical properties remain similar. We name these compounds using a systematic 3-step approach. First, count the carbons to find the base name. 3 carbons give us propane. Second, identify the functional group suffix. For a ketone, the suffix is 1. Third, check the first letter of the suffix. Since 1 starts with a vowel, we drop the final E from propane. Combining them gives us propanone. This system is used for every functional group. Using a 3-carbon base, we can derive the names propanol, propanal, propanoic acid, and even unsaturated forms like propene and propane. Remember that functional groups determine chemical reactions, while the length of the carbon chain determines physical properties like melting and boiling points. Carbon compounds are the literal architecture of our lives. They are the chemical basis of the food we consume, the clothes we wear, and the fuels that power the modern world. But the fundamental properties of these versatile molecules shift dramatically the very moment they are exposed to oxygen. When carbon meets oxygen, the reaction follows one of 2 distinct chemical trajectories. The first is a path of rapid decomposition. Here, oxygen reacts with the carbon to release the raw energy stored within its bonds, a process we see as fire. The second path is one of structural addition. Instead of breaking the molecule down, oxygen is integrated into the compound, transforming it into a new substance with entirely different properties. Distinguishing between these reactions is essential for predicting chemical behavior, understanding whether oxygen will act as an agent of total breakdown or a tool for precise molecular modification. Combustion represents the high-energy side of this relationship. It is the rapid oxidation of carbon that releases a characteristic burst of heat and light into the environment. We can track this across different fuels. Whether it is pure carbon, methane, or ethanol, the reaction with oxygen yields carbon dioxide and water, consistently generating heat as a primary byproduct. Yet the appearance isn't uniform. Some produce a sharp blue flame, while others burn with yellow smoke. This pressure stove shows the result of an ideal environment. When saturated hydrocarbons, carbon chains with only single bonds, react with a plentiful supply of oxygen, the combustion is complete. This efficiency is signaled by the clean blue flame. If the oxygen supply is constricted, or if the fuel is an unsaturated compound with double or triple bonds, the reaction is incomplete. Unburned carbon particles remain, glowing yellow and releasing black soot. This has direct practical implications. If your cooking vessels are becoming blackened on the outside, it is a sign that the air holes in your stove are blocked, leading to wasted fuel through incomplete combustion. This also explains the difference between a wood fire and a pile of charcoal. One produces a leaping flame, the other merely glows red. As seen in this image, charcoal lacks a visible flame because a flame is only produced when gaseous substances are burning. Because charcoal has already lost its volatile gaseous components, it simply glows as it releases heat. The visual characteristics of a fire provide a real-time report on the chemistry at play, revealing the efficiency of the reaction and the exact availability of oxygen. The second path offers a different outcome, adding oxygen to a molecule without destroying its primary structure. This is known as chemical oxidation. In a laboratory, we can demonstrate this by warming ethanol and adding an alkaline solution of potassium permanganate drop by drop. Potassium permanganate has a deep, rich purple hue, but as it enters the ethanol, the color disappears instantly. The purple color fades because the potassium permanganate is actively transferring its oxygen atoms to the ethanol molecules. Chemicals capable of this transfer are called oxidizing agents. By using substances like potassium permanganate or acidified potassium dichromate, we can force oxygen into the ethanol structure, converting the alcohol into ethanoic acid. Once the ethanol is fully oxidized, the chemical exchange reaches its limit.
Any further drops of the agent will cause the purple color to persist, signaling that the transformation is complete. Controlled oxidation allows us to treat oxygen as a precise chemical component, enabling the synthesis of complex new molecules rather than their destruction. These two paths, destruction for energy and precise transformation, scale from the lab to the global economy. This historical oil field represents the massive scale at which we extract carbon-based fuels to burn for energy. When we burn these fuels, oxygen reacts with everything in the mixture, not just the carbon, but also the nitrogen and sulfur impurities trapped inside. This simultaneous oxidation creates the nitrogen and sulfur oxides that drive modern air pollution. Understanding these reactions allows us to categorize the fundamental ways oxygen and carbon interact. On one side, we have combustion, a rapid, total breakdown of the molecule designed to maximize the release of heat and light. On the other, we have oxidation, a controlled process that uses chemical agents to preserve the carbon chain while carefully adding oxygen atoms. Ultimately, whether carbon provides the energy to drive our machines or the chemical structure to build our materials depends entirely on how we manage its relationship with oxygen. Look at these two molecules on screen. Their structural difference, specifically whether they use single or double bonds, dictates exactly how they react with other chemicals. We can group these reactions into two main types: addition for unsaturated molecules and substitution for saturated ones. It comes down to how full the molecule is. If a carbon chain has extra room, it will happily add new atoms. But if every single bonding slot is already taken, any incoming atom has to forcibly swap places with an existing one. Here is ethene, an unsaturated hydrocarbon. Its central double bond is a vulnerable space. During an addition reaction, one bond breaks open, leaving two empty bonding sites. A hydrogen molecule approaches, splits, and the atoms snap into the open docks. This requires a specific catalyst, like nickel or palladium, to force the reaction to proceed. This microscopic addition mechanism is exactly how the food industry operates. Manufacturers use a nickel catalyst to add hydrogen to liquid, unsaturated vegetable oils, turning them into solid, saturated, animal-like fats for cooking. Now look at methane, a fully saturated molecule. Every valency is filled by a hydrogen atom, leaving no room to add anything. So an incoming chlorine molecule has to aggressively swap places. Triggered by direct sunlight, one hydrogen atom is kicked off, and a chlorine atom takes its place. This chain reaction replaces hydrogens one by one until you get carbon tetrachloride. Saturated hydrocarbons are usually quite unreactive and inert when exposed to most chemicals. This sunlight-driven substitution is a unique, forced exception to that rule. Let's examine a specific carbon compound you encounter every day. This diagram shows ethanol, C2H5OH. It's a liquid at room temperature. It dissolves perfectly in water, and it's an excellent solvent used in medicines like cough syrups and iodine tinctures. While diluted ethanol is common, drinking pure, absolute alcohol can be lethal. For industrial uses, manufacturers actively denature it by adding poisonous methanol and blue dye to ensure it isn't consumed. If you drop an active metal like sodium into ethanol, it reacts immediately. The sodium displaces the hydrogen in the alcohol, and you can physically see effervescence as hydrogen gas rapidly bubbles to the surface. Watch what happens when we heat ethanol to 443 Kelvin and add concentrated sulfuric acid. The concentrated sulfuric acid acts as a dehydrating agent. It physically rips an oxygen and two hydrogen atoms out of the ethanol molecule to form water. To stabilize, the remaining carbon atoms are forced to snap together, forming a double bond. By stealing that water, the acid chemically forces a saturated alcohol to become an unsaturated ethene molecule. It's essentially the mechanical reverse of the addition reaction we saw earlier. Our next major compound is ethanoic acid, shown here with its defining carboxylic acid group. Pure ethanoic acid is known as glacial acetic acid because it freezes easily in winter. If you dilute it in water to about 5 to 8%, you get everyday vinegar. When you place this ethanoic acid next to absolute ethanol and add an acid catalyst, you trigger a process called esterification. The two molecules physically merge, ejecting a molecule of water in the process. The resulting compound is an ester, which typically has a very sweet smell and is widely used to make perfumes and artificial flavorings. Let's test your intuition. If ethanoic acid reacts with a base like sodium carbonate, what specific gas do you think is evolved? Think about how acids react with carbonates. The reaction produces a salt, water, and carbon dioxide. We know it's CO2 because if you pass that evolved gas through a freshly prepared test tube of lime water, it instantly turns milky white. Generating carbon dioxide gas from a carbonate is a defining characteristic of carboxylic acids, which gives us a highly specific test for identifying them. Let's put these tools to work. This matrix compares ethanol and ethanoic acid. Ethanol is neutral, while ethanoic acid has an acidic pH. Both, however, react with active sodium metal to produce hydrogen gas. Notice that identical hydrogen gas result. If you have an unlabeled beaker in the lab, dropping sodium in it won't help you tell these two liquids apart. They both bubble. That's where the sodium carbonate test comes in. Add it to the ethanol, and absolutely nothing happens. Add it to the ethanoic acid, and you get that distinct carbon dioxide bubbling. Using sodium carbonate to isolate the CO2 reaction provides the specific chemical evidence needed to identify a carboxylic acid when other properties look identical.
Look at this photo from the mid-20th century. Washing clothes has always been a battle of brute force against dirt. But when it comes to oil or grease stains, all the elbow grease in the world won't save you. This happens because of a strict rule of molecular physics. Water is an incredibly effective solvent, but it physically repels hydrocarbons like cooking oil. You can agitate the fabric or scrub it against a washboard for hours. The water molecules will simply slide right past the oil, leaving the stain completely intact. To break that barrier, you need a very specific type of chemical diplomat, something built to negotiate between two substances that naturally hate each other. Enter soap. Chemically speaking, soap is the sodium or potassium salt of a long-chain carboxylic acid. Removing a stain isn't about beating the fabric into submission. It is an act of chemical engineering, using a tailored carbon molecule to force oil and water to mix. To see how this works, we can look at this diagram of a single soap molecule. Notice how it is split into two very distinct halves. On one side, you have a long, zigzagging carbon tail, and on the other, an ionic head. These two halves have completely opposite personalities. The carbon tail is hydrophobic. It aggressively avoids water and seeks out oil. Meanwhile, that ionic head is hydrophilic, meaning it readily interacts with water. Drop these into a washing machine, and the hydrophobic tails immediately seek out the oil droplet, burying themselves inside it to escape the surrounding water. Because the ionic heads want to stay in the water, thousands of these soap molecules naturally align to form a complete enclosed spherical cage around the oil. This structure is called a micelle. The oil is now trapped in an emulsion, safely suspended inside this tiny molecular submarine. When the rinse cycle hits, the water grabs the hydrophilic heads and pulls the entire structure down the drain. The micelle shows exactly why carbon chains are so useful. By leveraging their specific physical traits, we can construct a molecular cage that solves an otherwise impossible physical problem. But this elegant system has a catch. Depending on where you live, the water coming out of your tap might be hard, meaning it carries a heavy load of dissolved calcium and magnesium ions. Those dissolved metals are highly reactive. When they bump into traditional soap molecules, they instantly bind with the ionic heads long before any micelles can form. When that happens, you get this reaction. The soap and the metal ions fuse into a solid, insoluble precipitate that we usually call scum. All your soap ends up bound into these useless curds floating in the water. No lather forms, no micelles are built, and the grease stays exactly where it was. To fix this, chemists tweaked the molecule's design, creating modern detergents. Instead of a carboxylic acid, detergents are typically salts of sulfonic acids. That single swap of the functional head makes all the difference. The charged ends of sulfonic acids do not react with calcium or magnesium, which means they remain fully effective in the hardest water. By changing just one functional group on a molecule, you bypass a major environmental limitation and completely alter its real-world utility. To understand how we can customize molecules like detergents, we must strip them down to their bare architectural foundation, the carbon atom itself.
This is methane, showing carbon's first major rule, tetravalency. It forms 4 stable covalent bonds by sharing its valence electrons with other atoms. But its second rule, catenation, makes it unique. Carbon atoms link endlessly, rapidly building massive chains, branches, and interlocking rings. If the carbon atoms are connected entirely by single bonds, the chain is saturated. If there are double or triple bonds between the carbons, it's considered an unsaturated compound. We can even convert an unsaturated carbon chain into a saturated one by forcing it to react with hydrogen gas and a catalyst. This process is called hydrogenation, and it's exactly how the food industry processes liquid vegetable oils. Tetravalency and catenation provide near infinite structural flexibility. They are the chemical rules that allow us to construct everything from the fuel in your car to the detergent in your laundry. Once you have a carbon chain, you give it a specific job by attaching functional groups to it. 2 critical ones are alcohols, marked by an OH group, and carboxylic acids, marked by a COOH group. These chemical categories exist far beyond the laboratory. Take this sugarcane harvest. It is the primary biological source for industrial ethanol production. Combining ethanol, ethanoic acid, and a catalyst produces water and a sweet-smelling ester. But treating that ester with a strong base like sodium hydroxide snaps it apart into an alcohol and a carboxylic acid salt, our original soap molecule, in a process called saponification. 2 more reactions to keep in mind. Drop sodium metal into ethanol, and it rapidly evolves hydrogen gas. Mix ethanoic acid with sodium carbonate, and it produces a salt, water, and bubbles of carbon dioxide. Mastering these equations provides a direct look at the molecular source code governing our physical world. Understanding how these elements link and react is a study of reality itself.